So in EDC, first we will study about the basic concept, then we will move for the deep concept of electronics devices. First is the classification of temperature. There are three types mainly. Absolute temperature is at 0 Kelvin. 0 Kelvin means minus 273 degrees Celsius. Room temperature is 300 Kelvin, that will be equal to 27 degrees Celsius. So while designing the any devices, electronic devices, most of them we are using will be at the room temperature. So we will see at this room temperature means at 300 Kelvin, that is 27 degrees Celsius, our device should perform the best so that everyone can use it. Next is the ambient temperature. Ambient temperature is 290 degree, so 290 Kelvin, that is 70 degrees Celsius, and this is for the communication system and superficial conditions, right? So temperature in Kelvin will be equal to temperature in Celsius plus 270 degree 270. So degree Kelvin is equal to, we can say Kelvin also, there is no problem. Now we will see volt equivalent of temperature, Vt, or thermal voltage. Thermal voltage Vt is equal to k bar T upon Q, where Q is charge of electron, 1.6 into 10 to the power minus 19 coulomb, and T is the temperature in Kelvin. K bar is equal to Boltzmann constant, that will be 1.38 into 10 to the power minus 23 joules per degree Kelvin. And while putting the value of k bar and q, we can get Vt is equal to T upon 11,600 volt. So from here we can see Vt is directly proportional to T. If T is equal to 0 Kelvin, our Vt will be the 0, but when T is 300K, 300K means at room temperature, Vt will be 300 upon 11,600, that will be 0.02586 volt, that will be 26 millivolt. The standard room temperature corresponding to a voltage of 26 millivolt. This is the important 26 millivolt. Sometimes we can also use it like approximately Vt is 25 millivolt. For a large variation in temperature, the variation in thermal voltage is negligible. Boltzmann constant already discussed, k bar is equal to 1.38 into 10 to the power minus 23 joule per Kelvin. If I want to change the unit from joule to Kelvin, joule per degree Kelvin to electron volt per Kelvin, so K will be 8.62 into 10 to the power minus 5 electron volt per degree Kelvin. From this K bar and K, from while changing the conversion for unit, we can say K bar is equal to 1.6 into 10 to the power minus 19 K. Right, so Vt is equal to k bar T upon Q is equal to capital, not capital, it's Kt, where K is here, K is in EV per degree Kelvin. So we can also find Kt is equal to by putting K is what, 8.62 into 10 to the power minus 25, and our temperature, let's say for the room temperature 300, so it will be same 0.02586 electron volt. No need for conversion from electron volt to volt. So in the later discussion we will study about some concept of surface potential. For now it's phi s is equal to Kt ln Na upon Ni electron volt. If you want to change it in the volt, there will be Vt ln Na upon Ni. No need to conversion of electron volt to volt here. In general, to convert electron volt to volt, divide it by Q. So now we will see electron volt EV. It is the practical unit of energy in electronics. 1 electron volt is equal to 1.6 into 10 to the power minus 19 joule. Energy gap EG or EG, that will be the, we will denote energy gap, band gap by EG, G capital or small. There will be conduction band, then EG, then VV. We can say EG is the forbidden energy band. Electron can pass through it, but can't be in this region. Okay, in this region, electron can pass. Electron can pass through it, but it can't be in this region. So this is the forbidden energy band only for intrinsic semiconductor, but for n-type and p-type this is not valid. Okay, for n-type and p-type this is not valid. In an atom, and the outermost orbit is called valence band, and maximum valency electrons are 8. There is nucleus, orbit is plus n, n is equal to 1, 2, 3, 4, 5. Then let's say after the outer orbit, there will be valence band. This is the EG band gap, and then conduction band will be there. So conduction band is actually the imaginary. The energy of the conduction band is greater than the energy of the valence band, we can say through the figure itself. Now let's see from factual things. Find out after experimenting with this all thing. So EG is equal for germanium is equal to 0.785 electron volt, for silicon 1.2 electron volt, for gallium arsenide let's not discuss for now. It is for at now for the EG 300 means at the room temperature. Germanium has EG is equal to 0.72 electron volt, silicon 1.1 electron volt, and GaAs 1.42 electron volt. So in a semiconductor, EG decreases with temperature variation. So from here we can say EG is directly proportional to 1 upon temperature. There is absolute formula also for EG with respect to temperature. EGT is equal to EG0 minus B naught into T, that 2 will be in EV. For germanium, EGT is equal to, let's say for germanium, when I'm saying taking at 0 degree, then EGT will be for silicon, for germanium it will be 0.785. From here you can see germanium 0.785 minus B naught. A at this temperature is 2.33 into 10 to the power minus 4 for germanium, whereas for silicon EG naught is equal to 1.21 and B naught is 3.6 into 10 to the power minus 4 temperature. So from here we can also see T is equal to temperature in Kelvin, B naught is a material constant, and B naught is electron volt per degree Kelvin. For metals, EG is equal to 0 at T is equal to 0 Kelvin. For semiconductor, EG should be less than equal to 1.5 electron volt. For insulator, EG can be greater than 5 electron volt. If energy gap is small, the electron requires a smaller amount of additional energy to move from valence band to conduction band. The additional energy can be supplied to the electron by means of temperature or heat or light or field intensity. So what is the now we will study about the electric field intensity or field gradient or field intensity or field. By definition, electric field is equal to minus dV by dt volt per meter. So if by magnitude, if we are going to see, it will be the magnitude of voltage existence upon distance or spacing. So field intensity is always directed from positive of battery to negative of the battery, or from higher potential to lower potential. From here we can see at x is equal to 0, let's say at point A, here is x is equal to 0, we have negative potential. Let's say V is equal to 0 here, and highest potential is at VB. So at x is equal to 1 millimeter, VB is equal to 1 volt. So magnitude of field intensity at A and B will be the different. So we will see EA and EB will be what, right? So magnitude of electric field at end B will be VB upon XB. So VB we have 1 volt and XB is 1 millimeter. 1 millimeter is 1 into 10 to the power minus 3 meter. So we have EB is equal to 10 to the power 3 volt per meter. Now we want to find magnitude of field at C. C is a middle point. C is at middle point at x is equal to 0.g x is equal to 0.5 millimeter. So magnitude of field at the center of the bar, that is at point C, EC is equal to VC upon XC is equal to 0.5 volt upon 0.5 into 10 to the power minus 3 is equal to 10 to the power 3 voltmeter. So magnitude of field at end A is equal to V upon XA, 0 upon 0 not defined. So now mobility of charge carrier. We see mobility is defined as mu is equal to drift velocity upon field intensity. So mu is equal to Vd upon electric field. And its unit will be meter square per volt second or centimeter square per volt second. So drift velocity is the velocity of the charge carriers under electric field condition. It is the average velocity of the charge carriers. Vt is equal to Vmax plus Vmin by 2. Now we see the electron mobility, that is mobility of electron will be denoted as mu e or un, or hole mobility will be denoted by mu h or mu p. So we will see for the germanium, silicon and gallium arsenide. So electron mobility will be, electron mobility is 3800 centimeter square per volt second for germanium, and mu p will be 1800 centimeter square per volt second. So mu p upon mu n upon mu p will be 2.1. For silicon, mu n is 1300 and mu p is 500. So mu n upon mu p will be 2.6. For germanium arsenide, mu n is 5600 and mu p is 400. So mu n upon mu p will be greater than 14. A semiconductor having larger mobility generally have higher conductivity. Conductivity of GaAs is greater than germanium, and conductivity of germanium is greater than conductivity of silicon. Electron mobility is always greater than hole mobility, and therefore electron can travel faster than hole and also contribute a larger current when compared to the hole. The mobility of charge carrier always electron mobility is always greater than hole mobility, and therefore electron can travel faster than hole and also contribute a larger current when compared to the hole. The mobility of charge carrier always decreases with the temperature, and is given by equation mu is directly proportional to T to the power minus m, where m is equal to 2.54 electron and 2.74 hole in case of silicon, and m is equal to 1.66 for electron and 2.33 for hole in case of germanium. In a semiconductor, mobility of charge carrier is a function of temperature and doping concentration or impurity atoms. Mobility of charge carriers decreases with increase in temperature, increase in doping concentration or atom concentration. After the doping, the mobility of charge carriers reduces, but in the absence of any equation derived how to calculate mobility of electron and hole after the doping, when mobility of electron and hole before the doping is given, hence we are helpless and we always consider mobility of electron and hole will be same before and after the doping while solving the problem and circuit design. This is very important. So mobility versus temperature will be decreasing curve that is given. Mu is directly proportional to 2 to the power minus 3 by 2, and as we know mobility of electron is greater than mobility of hole. So here is the curve for mobility versus atomic concentration. Mu versus electrical for semiconductor. Experimentally plotted graph is mu versus, when we will say electric field, that is voltage per centimeter. For a smaller electric field, 10 to the power 3 volt per centimeter, mu will be almost like constant, and between 10 to the power 3 to 10 to the power 4 it will be decreasing. Mu will be directly proportional to 1 upon root E, and from larger electric field, that is greater than 10 to the power 4, mu will be 1 upon electric field. For a smaller field intensity applied to the semiconductor, mobility remains constant, drift velocity linearly increases with the field. So Vd is equal to mu epsilon, mu E constant. For larger field intensity applied to semiconductor, mobility decreases, drift velocity enters into saturation. So Vd is equal to mu E. So if mu decrease, E is increasing, so Vd will be the constant. From the curve here we can see plotted for the Vd versus E. So for the a smaller E, we see here mobility, we see here mu versus G. For the smaller E, it is constant, mu is constant. Between 10 to the power 3 to the power 3, mu is equal to mu decreasing by mu directly proportional to 1 upon root E, and for the larger E, mu is directly proportional to mu 1 upon. So from here we can see, when we will plot now Vd up versus E, so we have a formula Vd is equal to mu E. So we know for the smaller E, mu is constant, so it will be varies linearly. It will be linearly from 10 to the power 3 to 10 to the power 4 E. It will be sublinearly, and after 10 to the power 4 Vd is saturated. So in a semiconductor, as field intensity are gradually increases, the drift velocity linearly increases, then sublinearly increases, then enters into saturation with larger field. Current, now we will define some basic concept. Current is defined as rate of change of charge with respect to time. I is equal to dq by dt, coulombs per second or ampere. In a semiconductor, there is a bipolar current is carried by two different charge carrier electrons and hole. Drift current, I drift, it is the current passing through the material or a device under the field intensity. Einstein equation is, in a semiconductor, dN upon mu n is equal to dP upon mu p is equal to Vt, or dN mu n upon dN is equal to mu p upon dP is equal to 1 upon Vt. It gives the relationship between diffusion constant. So here dN and dP are diffusion constant, and mu and mu p are the electron mobility and hole mobility, and Vt is our thermal voltage. So diffusion constant of charge carriers is D, also called diffusion coefficient. Electron diffusion constant dN, from formula here we can see dN is equal to mu n into Vt. Hole diffusion constant dP is equal to mu p into Vt. Unit for D is equal to centimeter square per second or meter square per second. Diffusion constant reduces with the temperature. This is important thing. D is equal to mu into Vt. So as the temperature increases, mu is R decreases, Vt is also increases. Vt is also increases, but mu is more increases. That's why we can say diffusion constant reduces with the temperature. dN upon dP is equal to mu 1 upon mu p. For germanium at temperature 300 Kelvin, dN is equal to 99 centimeter square per second, dP is equal to 47. So dN upon dP is equal to 2.1. How we are saying this? Because D is equal to D is equal to mu into Vt. So we can put the value of mu n and mu p, we can get it for different germanium and silicon. For silicon at T is equal to 300 Kelvin, dN is equal to 34 and dP is equal to 13. So dN upon dP is 2.6. Diffusion constant is a material parameter related with the property called diffusion. Now it is important concept, mass action law. Mass action law is Np is equal to Ni square. Np is equal to Ni square, where N is equal to concentration of electrons per unit volume or density of electrons per unit volume or number of electrons per unit volume, and P is equal to concentration of holes per unit volume or density of holes per unit volume or number of holes per unit volume. Ni is intrinsic concentration. In an extrinsic semiconductor, under thermal equilibrium, the product of electron and hole is always a constant and equal to a square of intrinsic concentration. Thermal equilibrium means at a constant temperature or at a given temperature, or temperature is kept constant. N increases by x, so it will be N into x. P decreases by x, so P upon x. The law is mainly used to calculate magnetic concentration in the semiconductor. N-type semiconductor majority carriers are electrons is equal to Nn. Magnetic carriers are holes. That's denoted by Pn. So from the mass action law we know N into P is equal to Ni square. So majority carriers concentration and magnetic carrier concentration we have denoted by Nn for N-type, and magnetic is holes. So while putting Nn into Pn is equal to Ni square, Pn will be Ni square upon Nn. Similarly, for the p-type semiconductor, majority carriers are holes denoted by Pp, magnetic carriers are electrons denoted by Np. So Np is equal to Ni square upon Pp. In a semiconductor, the electrons and hole concentration are N1 and P1 respectively. By adding impurity atoms into the semiconductor, the electrons and hole concentration are N2 and P2 respectively. Then following equations are applicable. N1 P1 is equal to N2 P2 is equal to Ni square. N1 P1 is equal to N2 P2. In a semiconductor, before doping and after doping, the product NP is always constant. Mass action law is not applicable for degenerate semiconductor. This is important. So while mass action law is N into P is equal to Ni square, it is not applicable for degenerate semiconductor. Ni square is equal to A naught t to the power 3 e to the power minus Eg naught upon Kt. We can also write it Ni is equal to root A naught t to the power 3 by 2 e to the power minus Eg naught upon 2 Kt. A naught is a material constant. A naught is equal to material constant and independent of temperature. Broadly we can see Ni is directly proportional to the power 3 and Ni is directly proportional to the power 3 by 2. Intrinsic concentration depends on temperature and energy gap Eg naught. When compared to silicon, intrinsic concentration is larger in germanium because of the smaller energy gap Eg naught. At 300 Kelvin for germanium, Ni is equal to 2.5 into 10 to the power 13, and for silicon Ni is 1.5 into 10 to the power 10 per centimeter cube. Wavelength of light lambda is equal to Hc upon Eg in meter. Eg is energy gap of the material in electron volt. H is equal to Planck's constant, that is 6.626 into 10 to the power minus 34 joule second. C is the speed of light in free space, 3 into 10 to the power 8 meter per second. Wavelength of visible light is in the range of lambda is equal to 0.38 micrometer to 0.76 micrometer. Any wavelength of light lambda greater than 0.76 micrometer belongs to infrared region. The maximum wavelength of light is given by lambda c, also called cutoff wavelength or critical wavelength. Lambda c is equal to 1.24 upon Eg, that will be in micrometer. Lambda c will be 1 upon Eg. A semiconductor having larger energy gap will have a smaller cutoff wavelength. Lambda c germanium is greater than lambda c silicon, greater than lambda c germanium arsenide. Lambda c is directly proportional to 1 upon Eg. So we have Eg for 300 Kelvin for germanium is 0.72 electron volt, silicon 1.1, GaAs is equal to 1.42 electron volt. When light falls on the semiconductor with wavelength less than lambda c, electron hole pairs are generated in the semiconductor. From the Gauss formula, we have the smallest lambda is for the violet color and largest lambda for the red color. To excite an electron from valence band to a conduction band, the photon energy should be greater than the forbidden energy band, like Eg, what we say. So h nu should be greater than or equal to Eg. For this lambda must be less than is equal to lambda critical. The photon energy supplied is less than Eg, electron hole pair is generated and electron will come out of the VB but unable to reach CP, and therefore it will fall back into the VB and covalent bond is completed. Resistivity rho or specific resistance of that material, unit for rho is equal to ohm centimeter or ohm meter. Intrinsic semiconductor for NTC of intrinsic semiconductor, it is NTC of R, means R decreases with increasing temperature because rho decreases with the temperature. We have formula for R is also rho L upon M. Conductivity is reciprocal of rho. Unit for conductivity sigma is equal to 1 upon ohm meter or ohm per meter, rho per meter. This is ohm 1 upon ohm meter, this is rho per meter. Conductivity denotes current carrying capacity of the material or device. So conductivity is carrier concentration into charge into mobility. Conductivity of variation in semiconductor may be due to variation in carrier concentration, variation in mobility. For intrinsic semiconductor, conductivity is NQ mu n plus PQ mu p rho per centimeter. As temperature increases, conductivity increases. And why so? Because we have seen as temperature increases, mu n will be decreases. But compared to mu n will be increases largely. Similarly, mu p will decrease somewhat, but p will increase. So overall conductivity increases with temperature. In intrinsic semiconductor, as temperature increases, mobility reduces, and this will reduce the conductivity by a small value, and at the same time, because of the temperature, a large number of covalent bonds will broken and large number of electron hole pairs are generated, and this will increase the conductivity by a large value, and the net result conductivity increases with temperature. This is experimentally found, right? In intrinsic semiconductor, conductivity mainly depends on carrier concentration. For metal or unipolar electrons, conductivity is NQ mu n rho per centimeter. In metal, free electrons concentration is independent of temperature. In metal, conductivity decreases with the temperature. Hence, metal are PTC of R. Resistance. Current density J. Current passing for unit cross sectional area. J is equal to I upon cross sectional area. In a semiconductor, J is equal to sigma E. E is electric field. Diffusion and diffusion current. The migration of charge carrier from higher concentration to lower concentration or from higher density to lower density is called diffusion. Diffusion is mainly due to the concentration gradient. Gradient is d upon dx. dn upon dx is electron concentration gradient, is electrons per centimeter cube per centimeter. dp upon dx is hole concentration gradient, is holes per centimeter cube per centimeter. Diffusion current flows only in semiconductor. Diffusion current flows only in the semiconductor due to unequal distribution of charge carrier. In semiconductor, diffusion is due to unequal distribution of charge carrier. This from here figure here say this is the high this region is higher concentration of electron or holes, but this is of region 1, region 2 lower concentration. So from here we have to formula length of diffusion is L denoted by L is equal to root under D into tau, where D is equal to diffusion constant will be D is equal to mu into Vt. So of final L is equal to root under mu Vt into tau. Length of diffusion of depends on mobility, temperature, carrier lifetime. Carrier lifetime is average lifetime of the charge carrier. Length of diffusion refers to the maximum length. Electron diffusion length will be denoted by Ln is equal to Dn into tau n will be is equal to mu n Vt into tau n. Similarly, for hole diffusion constant, it will be dp into tau p. dp will be mu p Vt into tau. So from here we can see diffusion of in this figure. At this region, electrons are at higher concentration. At this region, electrons are lower concentrated. So electrons follow from this region to this region. So this is the direction of diffusion of electrons n type. Similarly, for the p-type. At this diffusion of p-type semiconductor, holes are in majority concentration. So at this region we can see holes are majority mainly concentrated in this region, but in this region there are very less holes, so it diffuses from higher concentration to lower concentration. In diffusion current, density is the direction of x, then it is positive. If diffusion current density is opposite to the direction of x, then it is negative. So electron diffusion current density will be the negative, because we have dn, and dn upon dx is negative. Jn diffusion is equal to q dn into dn upon dx. Whole diffusion current density Jp will be the positive, is equal to minus q dp upon dx. In a semiconductor, the total diffusion current density will be the J diffusion from electron diffusion and P diffusion. So from here we can see J diffusion is Jn diffusion plus Jp diffusion. By putting Jn and Jp, we have J diffusion is q dn by dx, and since Jp is negative, is minus q dp by dx, so overall J will be q dn dnx minus q dpx. In a semiconductor electron diffusion current, In diffusion is equal to Jn diffusion into area. Let's denote area by A. So we have Jn is equal to q dn by dx. So after multiplying with A, Ri, it will be Ia. So Ia diffusion will be A q dn into dn by dx. Similarly for the Ip, but here Jp will be the negative, so here is the term negative thing is here. By default, always consider unit cross section area if nothing is given. Total current density in semiconductor will be the diffusion current density, current density due to electron and current density due to holes. We will denote it by J is equal to Jn plus Jp, but Jn itself will be due to drift and diffusion. So we now bifurcate it in two more division, that is we have total current density obviously Jn plus Jp, but Jn itself will be for the two reasons. First is the drift because of the voltage difference, and another is for the diffusion. This is for the concentration difference. So we have for the drift thing, for drift Jn is equal to conductivity of N and electric field. For diffusion, Jn will be q dn by dx, right? So now putting the value of everything, we have Jn is equal to Jn drift plus Jn diffusion. It will be sigma n A plus Jn diffusion, and so total Jn is equal to we have sigma n is equal to also sigma n is equal to n q mu n. Sigma p will be p q mu p. So after putting this, even for the Jp, we have sigma p e plus Jp diffusion, p q mu p e minus qp dp by x. By putting all this, we can see from here we have J final. In this is for the Jn, this is for the Jp. drift current and diffusion current. In a semiconductor, the total current I is equal to I due to electron and I due to holes. So I is equal to IN plus IP. IN is equal to IN drift plus IN diffusion. So IN drift will be area into NQ mu n E plus AQ dN by dx. Similarly for the IP is equal to IP drift plus IP diffusion. It will be A into P into Q into mu P E minus A into Q dP by dx amplitude in ampere, sorry. So in a semiconductor, drift current is due to carrier concentration, mobility of carriers, field intensity. Drift current is mainly due to electric field intensity. Diffusion current is mainly due to concentration gradient. Intrinsic semiconductor or pure semiconductor belongs to the fourth group of the periodic table. Crystalline structure of pure semiconductor at 0 Kelvin is it has valency 4 and 4 electrons we have 1 2 3 4. So if I share it with neighborhood, it has 4 valence electrons. The area 4 plus 4 8, so total 8 valence electrons per atom is there. Energy band diagram at 0 Kelvin is shown here. So at the 0 Kelvin, conduction band will be the empty, but valence band have 8 valence electrons per atom. The sharing of electron with the neighboring atom is called covalent bonding. In one covalent bond, there will be 2 valence electrons at 0 Kelvin. Every electron is in perfect covalent bonding. Hence, intrinsic semiconductor at 0 K will be working as a insulator. Crystalline structure at 300 Kelvin. So bond will be broken. There will be hole here. There will be hole here, trying to make bond with the electrons here. So at this temperature, some covalent bond will be broken. So electron hole pair will be generated. So some holes or some electrons generated will be goes to the conduction band. But we know as temperature increases, Ni is also increases. So when a covalent bond is broken, it will create one electron and one hole. The electron will be jumping from valence bond to conduction band and become free electrons, and hole will remain in the valence bond. Hole is the empty space created by the electron in the broken covalent bond. Hole is created because of electron. Hole is a carrier of current with positive charge of 1.6 into 10 power minus 90 coulomb. Electron and hole have equal and opposite charges. In intrinsic semiconductor, always Np is equal to P. That is the condition for intrinsic semiconductor is N is equal to P is equal to Ni. Current direction is opposite to the flow of the electron, or it is in the direction of hole flow. In semiconductor, because of opposite charges, electron and hole always move in the opposite direction. Let's say in the semiconductor from left to right, electron is moving. Let's say electron is moving from left to right. So our current will be right to left. Similarly, if our hole is moving from right to left, it will be for IP right to left. So overall I will be IN plus IP, that will be from right to left. Electron and hole. One more point here is, we can see IN is greater than IP because mu n is greater than mu p. Electron and hole always move in opposite direction. they contribute the current in the same direction. Important thing is here, electron and hole always move in opposite direction, but they contribute the current in same direction. Because of the convention, we are saying that current direction is the opposite of the electron direction. In semiconductor, electron will contributing the current from conduction band and holes will be contributing the current from valence band, and total current is the sum of the electron and hole current. Intrinsic conductivity sigma is equal to nq mu n plus pq mu p, but n is equal to p is equal to ni, so sigma is equal to niq mu n plus mu p. Ni is directly proportional to ni, but ni is directly proportional to 2 to the power 3 by 2. Hence, ni increases with the temperature. Intrinsic resistivity Pi is 1 upon ni. So, Pi is equal to rho I, actually. Rho I is equal to 1 upon ni q mu n plus mu p. Generation of electron hole pairs. Electron hole pairs generated because of the breaking of the covalent bond. Now, recombination thing. Of electrons pairing with a hole is called recombination. During recombination of free electrons and a hole will be lost and covalent bond is created. During recombination, the free electron will be falling from conduction band to valence bond. Higher energy level to lower energy level, and difference of this energy is released both in the form of heat and light. Carrier lifetime. It is the average time taken by the charge carrier from generation to recombination. It is the, or we can say in another word, it is the average time taken by the charge carrier from breaking of covalent bond until its recombination. Main disadvantages: negligible conductivity. Only device made from intrinsic semiconductor is PIN diode. Important. Hole is basically a valence electron. Valence electron means valency of electron, actually. Okay, so hole is viewed as a valence electron assumed with a positive charge. Hole is provided with a positive mass. And now here is a question. We have to calculate intrinsic conductivity and intrinsic resistivity. Conductivity sigma and resistivity rho I. That is for the intrinsic germanium at for germanium at 300 K. So assume Ni is equal to, for germanium we have 2.5 into 10 to the power 13 per centimeter cube. Mu n is 3800 centimeter square per v second, and mu p is equal to 1800 centimeter square per v second. So sigma I is equal to nq mu n plus pq mu n. In intrinsic, n is equal to p is equal to ni is equal to 2.5 into 10 to the power 13. So sigma I is equal to nq mu n plus mu p for intrinsic thing. That's what we have put at the value of 2.5 into 10 to the power 13 into 1.6 into 10 to the power minus 19 into mu n plus mu p, 3800 plus 1800. So we have total sigma I, that is conductivity, intrinsic conductivity is 0.0224 rho per centimeter. And when we are going for the intrinsic resistivity, it will be 1 upon conductivity. So it will be 1 upon 0.0224. That will be 44.64 centimeter. Similarly, now we have to calculate the conductivity and rho for the pure silicon at room temperature. So here one thing will vary, that is Ni. Ni will be now 1.5 into 10 to the power 10 per centimeter cube, and mu and mu p will be for the silicon 1300 and 500. So sigma I is equal to Niq into mu n plus mu p. By putting this value, we will get sigma I is 4.32 into 10 to the power minus 3, and rho I is equal to 1 upon sigma I is equal to 1.432 into 10 to the power minus 6 will be 231,481 ohms. Right.